All right, my friends, let's jump into some concrete lateral design. So I just wanted to point out that not every shear wall comes with a couch in front of it, but if you spec it out in the plans, that'll be included in the original bid. Okay, so there's a drastic difference between wind and seismic forces, and it just depends on, or they depend on completely different elements. So for wind, it depends on these things. So where it is, site exposure, the building shape, and height. For seismic, the nature of the vent, the ground motions are different in different places, or different earthquakes, depending on the type of earthquake and the soils at your site. Then the building weight and the rigidity of the system, which relates to shape and height, but mainly weight and rigidity are the drivers for seismic in addition to the ground motion. Okay, load pass in gravity loads or gravity load paths, the forces just run downward through the building and then get resisted upward by the foundations. And they can be fairly, I guess, easier to understand than lateral forces for some people. And it's okay if you struggle with it. One of the analogies I've heard over the years is seismic is like taking the building, turning it 90 degrees, and cantilevering it off of the imaginary wall. So in this case, the foundations act like the cantilever support, and then the forces will work their way through, in this case, the lateral bracing or the vertical bracing in the building to the foundation. So this slide here kind of elucidates that a little bit better. Okay, so what happens is the forces enter the building. So wind may push on the building, seismic may create inertial forces in the wall, cladding, or panels. There's inertial forces in the diaphragm. Similarly, the wind forces will push on the diaphragm. Diaphragms are like big, deep beams. Those will carry the forces to the shear walls, brace frames, or moment frames, or whatever other lateral element you have. And those forces will work their way down to the foundation, come out as a base shear, and some type of overturning. So depending on the magnitude of the forces, the weight of the building, you may get quite substantial uplift in the foundations, which then needs to be either a deep foundation system or enough mass in the foundation to resist that. So it's all kind of a game of how much force, how much weight when you get to the foundation to keep them stable. So getting into diaphragms, we can think of them like deep beams. So in this case, we have our diaphragm, which would be the floor plate. These lines would be lateral vertical elements like shear walls or brace frames. And what's important to remember is they don't always occur at the end of the building. So if we go back to this building, there may be a lateral element in here, and that's all cool. A lot of times we need multiple internal frames to keep the building stable. So if we treat it like a beam, we can analyze it like a beam. So if we come here, we can basically calculate the shear, or do a shear diagram like we normally would. We can do a moment diagram, and then we'll look at unit shear. Usually that's the easiest units to work in. And then a tension and compression in the chord due to the moment. So we can calculate that just by dividing the moment we calc here by the depth, W, here. And then we can size the unit shear of the concrete here. And then for tension and compression, we may have something like this where we put some extra rebar in the boundary near the edge. And if the stresses are high enough, greater than 0.2 F prime C, we'll put hoops in. Anyway, so hopefully that's a helpful introduction, and then there's a shear equation for it and some limits. Okay, shear wall systems, we basically have a cantilevered wall sticking up out of the ground. Sometimes these might be coupled to other walls, so we could have a wall over here and then maybe coupling beams between them. Essentially, they pick up the diaphragm shears at each level, push back with the shear at each level, and then we have a tension and compression couple at the bottom and a sliding resistance at the bottom. So we basically, to size the boundary still, we find the moment from these forces, remembering to use their full moment arm, and then divide by the distance between those two couples, or those two resultant forces. Shear walls are extremely efficient, both from a material usage and just general seismic performance. The downside is they tend to block windows and openings and whatnot, so it takes a little more coordination with them, with the architect, to make sure things are laid out properly. Okay, moment frames are quite popular because they promote the use of windows and open floor plans, which is super important to architects. So in a moment frame, the lateral forces are applied, and then the joints are rigidly connected. And for cast in place concrete, this is fantastic because concrete, when it's cast in place, those rigid joints are just inherently formed. Whereas in a steel building, you have to make those moment connections, and that's tremendously cost and time intensive. But done. All right, here's an example of a dual system where the perimeter is a moment frame. You can see how big those columns are. And that was done for both progressive collapse resistance and to carry wind and seismic forces. And then internal to here, you can see this little white thing was an internal shear wall. And those shear walls reduced the size of these perimeter moment frames and just gave this building some extra redundancy, which was important for the client. It also sped up the schedule 6 months because we didn't have to wait for massive columns to be shipped from overseas. Okay, R factors. So for special moment frames in the seismic equation, we would divide by 8. And as we talked, or I guess we didn't talk, when we do that, we need to make sure, I think this slide's out of order. Where did that go? Anyway, we need to make sure that we absorb energy. So if we remain in the elastic region, that's cool for wind and what we really want to do or need to do. But in seismic, when we divide by 8, our force is super low, but we need to make sure our materials and our configuration can yield and absorb energy. So when you plot stress versus strain, the area under the curve is the energy. So that's an important aspect of this whole deal. Okay, I've also added some slides on irregularities. So if we have reentrant corners, big openings, we need to address that by making things compatible. So for this case here, I have a moment frame along here, but shear walls on the other sides. Maybe we change this to a brace frame so it's similar stiffness. Where did that? That's weird. Anyways, for vertical irregularities, we have a similar thing going on. So if we have a brace frame that goes to a moment frame or a brace frame that's staggered, we either need to design for higher forces per the code requirements or stack them. It's always better to have good layout. And that's something that you can talk to an architect and say, hey, look, if we have poor layout here, I'm going to have to bump up the forces 30% up to 300%, depending on what's going on. So that can be kind of a sell to them. They're not. It's not really effective to go to an architect and say, "Hey, for all these technical reasons, we need to do this." Put it in simple terms: schedule, cost, and that speaks volumes. Okay. A little bit on seismic force equations and then drift. So drift limits prevent non-structural elements from getting damaged as much. So what we're talking about in drift is from one story to a next, how much are they relatively displacing to each other or relative to each other. And the requirements are given here. I've put a table where I've calculated some of that for different heights. It's important to remember to multiply your calculated drift by the CD factor, which you get from the table with the R factors out of ASC 7. Okay, and then the elements of a seismic building that aren't moment frames or shear walls that are specifically detailed for seismic forces still have to meet certain detailing requirements. So if we look at this column here, you can see it's completely destroyed. It doesn't really carry much vertical load, probably none at all at this point. And then this column here, even though the cover's gone, you can see the spiral hoops inside of that have kept that column together to the point it can carry vertical load, even though laterally this building's pretty thrashed. So in this case, the building will probably be torn down, but it's still standing because of those ties, and people can get out. And that's really the key provision of Section 18.4 is how do we detail the other elements in the building to remain stable. Okay, finally, for the shear wall provisions, rather than pulling them out of the code and putting them here, I've decided to give you guys and gals the opportunity to dig into the code more deeply than probably you have at this point. So at this point, I'm going to turn you loose to jump into the code, pull out the provisions, and design your wall. And then as you get to your questions and get stuck potentially, we'll talk more in class about it. So good luck with that, and same for moment frames. I want you to jump in, look at that, understand the provisions, and kind of comprehend that more deeply. All right, good luck with that all, and we shall talk more in class as we do always.